We're going to continue on to talk about solving ax equal to b, and one of the methods we're going to use now is what's called the LU decomposition, which is a kind of a really powerful technique for trying to bring the operation count of solving ax equal to b down so that we can actually solve systems in which you have the same a used repeatedly, and we can make this much more efficient using this decomposition technique. All the course notes, extra videos for this can be found here at the website, so you can link it there. It's also in the description below so that you can have access to additional information. So let's talk about a LU decomposition. In general, decompositions of matrices have formed the backbone for quite a long time, decades, of how we might solve linear algebra systems or systems of equation at scale much more quickly. LU is a classic technique which basically takes the matrix A and decomposes it into a product of two matrices, L and U. So if we generically take a 3 by 3, here it is, the structure of L and U is very special. Specifically, the structure of L and U is such that L itself is given by here. It's a lower triangular, so notice it's got 0 on the upper triangular area, 1s down the diagonal, and the matrix U is upper triangular, so you have all these values up here, and then in the lower triangle you have zeros. What we're going to do is, if we can get this decomposition, you'll see that we can now solve ax equal to b much more rapidly than trying to do Gaussian elimination at each point. Okay? Right up front, what I'll tell you is constructing the LU decomposition is actually an order n cubed operation, but once you have it, solving the system becomes order n squared thereafter. So it's a one-time costly operation followed by execution at order n squared, which is quite a bit less. As n gets large, you definitely want to scale at n squared versus n cubed. So let's talk about how this is advantageous, because the LU decomposition basically is structured around saying I have x equal to b, there it is, and what I really want to do with x equal to b, I'd like to decompose it here. The a becomes LU, so there's the LU, x is equal to b. Now what we're going to do in this is we're going to actually define u of x here to be a vector y. So I have u of x equal to y, and then if that's y, then I have ly equal to b. So notice what we've done here. We've taken one linear system of equations, which is ax equal to b, and I've now broken it into two pieces here, ly equals b, ux equal to y over here. So we've broken it into two systems of equations. But these two systems of equations that we have here actually are quite advantageous. So let me show you how this works. Remember that the L is lower triangular, U is upper triangular. And we can take advantage of this in the solution technique because essentially to find the vector y that we need in ux equals, or uy equals x, we can basically solve for y just by forward substitution. So the way it's structured, these are the equations that you get out of this. Okay? 1, y1 is equal to b1. Then what you find is m21, y1 plus y2 is b2. m31, y1 equals y2, y3, b3. So notice this is forward substitution because the first one already tells you what y1 is. You can bring it down here to the second equation to solve for y2. Then you can bring it down here to the third equation to solve for y3. So y1 and y2, y3 are all basically found in this forward substitution algorithm. So this is quite nice because now what you have is because it's in this lower triangular form, the forward substitution just simply is an algorithm for filling in all the values starting from y1 all the way to y of n. Okay, so let's go now to what we have left over, which is ux equal to y. Now that we have the y vector, then we can do back substitution like what we learned when we did Gaussian elimination. Once you get it into this form, what you find is an equation here for x3 in terms of y3 and u33. So you can get x3, bring it up a level, solve for x2 because now you have x3. Now that you have x2 and x3, bring it up here to get x1. So essentially what this means is you do a forward substitution to get y, the backward substitution to get x. So we're solving two linear systems of equations, but because they have this very nice form, it makes it very easy for us to get the solution. The important thing is both of these operations are order n squared. Once we have this decomposition, once I have L and U, then each one of these pieces is an order n squared operation. And so that's the advantage of having this LU decomposition, because I'm basically getting around the order n cubed that I have to do for Gaussian elimination. Of course, this is assuming we have L and U, and we're going to talk about how we get L and U, because that actually is a one-time cost of order n cubed, and then after that we can use it at order n squared. So really the advantages. The advantages are what I just showed you in LU. It's basically you're saying I'm going to do two n squared operations, which is basically n squared, versus Gaussian elimination, which scales roughly like n cubed. Right? So if I have a 1,000 by 1,000 matrix, then LU would be 1,000 times faster to get a solution for it. So this is why we want to use a technique like LU decomposition, because it's very fast in comparison to Gaussian elimination. Of course, we have to have those two matrices L and U to accomplish this task, and so we're going to talk about how do we go about doing it, because it very much looks like a Gaussian elimination to get the L and the U. Again, oftentimes when we solve these AX equal to B systems, we're solving that AX equal to B system repeatedly, where we keep changing the right-hand side B. And so we just keep solving it over and over again where we're changing B, so that means I could do this decomposition of A once, and then after I've done it once, then I can use it at order n squared like I'm showing here. So let me first review Gaussian elimination, because we've done it in the previous lecture, and in fact if you haven't seen that, I encourage you to go back, watch the Gaussian elimination just so you understand both the algorithm and operation count associated with it. I'll review it briefly here because we're going to use the same kind of architecture to get our LU. So the idea is we write an augmented matrix, AX equal to B in this form, matrix A with a bar B. We start off with a pivot, and what we're going to do is walk down the pivots, and for each pivot we're going to try to make the rows that are directly below it 0. Okay? Those values just below it 0. So in this case here we have basically 3 equations, and to make those 0 I can just simply say subtract the second equation, take the second equation, subtract the first from it, take the third equation, subtract the first from it, and once you do that, then you're getting yourself into a situation where you now have zeros here, and now what we can do is move to the next pivot. You can actually even take that third equation, divide by 2, and now you have these 2 equations, allowing you to take the third row, subtract the second from it, which then gives you your final Gaussian eliminated form here, which this looks a lot like our U vector that we're trying to construct. Okay? And then you back substitute. So that was the idea of Gaussian elimination, right? Put it in upper triangular form, and that costs you order n cubed because you have to walk through all the diagonal elements, and for each diagonal element you have to go down for each row and across all those columns. So order n cubed operation gives it into this form, and then you're just doing back substitution. So LU is going to be very much like Gaussian elimination. We're going to try to put our matrix in upper triangular form, but the way we're going to write this is we're going to take a generic matrix A and write it as the identity times A. We know that if we multiply anything by the identity, then it comes out to be basically the same matrix as given back. But we're explicitly going to write out the identity times the matrix A. So what I'm going to do is walk through how we might do this with Gaussian elimination. So the first thing we're going to do is do exactly like what we did before. We're going to pick a pivot. Here's the pivot, top diagonal term, and we're going to walk down the pivots. And what we're going to try to do is we have to pick a pattern by which we're going to do the elimination. What I mean by a pattern is, before, we could say we could add or subtract any rows or columns or multiply by any constants, and we didn't worry about if we had any consistent scheme to do that. Now what we want to do is have a consistent scheme to do this. In particular, the scheme we're going to use is we're going to figure out how do I make the diagonal term the same as the term I'm going to eliminate. So I have a -2 here, a 4 here. So I can multiply this top equation by -1/2. If I multiply by this -1/2, this 4 becomes -2, just like this one here. Same thing when I'm going to try to eliminate here to get this to be a 0. This is a 1, this is a 4. All I have to do is multiply that row by 1/4. That's denoted over here. Okay? So that factor of -1/2 and that factor of 1/4 actually end up right here is the -1/2. That's where I'm going to eliminate the -2. And the 1/4 is right here where I'm going to eliminate the 1. So these two terms corresponding to the elimination of these two terms here are making them 0. Okay, so I put those factors there, and then once I've done this, I'm going to take the row that I'm trying to eliminate, subtract my pivot row from it. Now if I do that, I end up with this row here. So you can do the calculation. Again, take this row, subtract the first one from it. After I've multiplied by -1/2, you will end up with a new row where, again, I've eliminated the 0 here. Same thing we do to the third row. We take the third row and we subtract the pivot row from it, multiply by 1/4. Again, if I multiply by 1/4, this will become 1. And I'm going to take 1 minus 1, which gives the 0 here, and this is what I get. So that's step 1 in this LU decomposition. So you can see it's very much like Gaussian elimination. It is Gaussian elimination, but now with a fixed pattern for an elimination. So I have to apply that pattern throughout the entire decomposition process. So that's going to give us this, and again, I just want to point out the numbers here, -1/2 and 1/4, they follow directly from what I had to do the elimination. Let's go to the next step in the Gaussian elimination, which is now to pick this as my pivot and try to eliminate this here. So what do I have to multiply the pivot by so that this number is exactly the same as this here? I have to just multiply by -1/2. Right? So if I multiply -2.5 by -1/2, it becomes 1.25, which is exactly the term I have here. So this -1/2 ends up here in this matrix here. And then when I do this, I take this row here, third row, and I subtract the pivot row from it after I've multiplied the -1/2, and I end up with this row here. So notice what I've done. In this process of Gaussian elimination, I've ended up with an L matrix and a U matrix. So in fact, that's exactly what we have at the end of this decomposition are the two matrices that we require. Okay? So again, the process was just like Gaussian elimination, except now I'm keeping track of the scalars that I had to multiply each row by in order to do the elimination. And those scalars ended up here in the L matrix, and the U is basically setting me up to have an upper triangular form. So that's the idea of this. And as far as the operation count goes, again, it's order n cubed once. Once I have these for a matrix A, I don't have to do it again. So every time after that is order n squared. So you pay an upfront cost, but now you keep using it. And there's a lot of matrices where we would construct the LU decomposition, and then we would just simply use them thereafter if we're solving a system where we're continually updating the values of B and requiring extra solutions. Okay, one issue that we have to address immediately is when we do this LU decomposition, remember I just had the matrix A and I just decomposed it. But what happens if I have a 0 pivot? So when we did Gaussian elimination, if you have a 0 pivot, that means you've got to trade some rows. Okay? You want to trade out that 0 pivot for a non-zero pivot. So you're going to look at the rows below you and then try to trade that out. Now A, when we do the LU decomposition, is all by itself. And so when you're solving AX equal to B, if you're trading rows in A, you have to trade rows in B. And so what we want to actually think about is not just solving AX equal to B, but there is some permutation matrix P that switches rows so that I don't have any zero pivots. Let's call this permutation matrix P. So really what I want to think about is AX equal to B, and I want to multiply both sides of this equation by matrix P, which is a permutation matrix. So PA X equals PB, and all this P does is it switches rows. Okay? And by the way, a permutation matrix, if I wanted to switch, for instance, the first and second row, I just take the identity matrix and take the first row of the identity, switch it with the second row of the identity matrix. Now, any matrix I multiply that by will switch the first and second row. So that's what a permutation matrix does. It tells you, if I multiply by this P, it just simply switches rows. And that's exactly what we need here in a more general context. Now, by the way, if we never had to switch any rows, then P can just be the identity. Okay? But if we did have to switch some rows, then P tells you which ones. Maybe the j and kth rows switch, so that means the j and kth rows of the identity switch, and that's the mapping for us to make sure we have a self-consistent solution. So once I multiply by this permutation matrix, then what I have is PLUX is equal to PB. So actually what MATLAB or Python does is once you've done the switching, now the LU acts on PB. In other words, the switches of B. Okay? So here's how you might do this in MATLAB or Python. So mostly here what we're going to do is first just show you how to solve these in the simple way and then talk about the LU decomposition second. So here you go, Python code. You start off import numpy as MP, and then you make, let's say, a 3x3 system of equations. A is an MP array, and here is a 3x3 system. 1, 1, 1, 1, 2, 4, 1, 3, 9. That's the third row. So I have a 3x3 matrix. The right-hand side B is the following MP array, 1, minus 1, 1. Okay? So what we have is AX equal to B for a 3x3 system, and if you want to solve it, it is as simple as this command here. X is equal MP, lin algebra, okay, so this is calling the linear algebra package, dot solve A comma B. So you put in A comma B, it gives you back the solution X of AX equal to B. Okay, so pretty easy to solve these. MATLAB code is similar. You define the matrix A, find the matrix B, and notice down here, this is fantastic. The backslash is a linear solver. So A backslash B means give me the X values. Now, by the way, the backslash is quite a sophisticated algorithm. So we will talk about it a little bit. There's more details in the notes about it. But really what it does, it actually first just even checks to see if it's an upper and lower triangular form so that it can actually just do back substitution or forward substitution. Or even it looks to see, can I just permute it to put it in upper and lower triangular form? And then it will do the operations in order n squared. So quite a sophisticated algorithm. Solve is more of a brute force algorithm, just Gaussian eliminates and gets you the solution. And so these are two ways to just solve X equal to B. And again, the economy of characters, because MATLAB basically assumes this is the most efficient thing you're doing in MATLAB, which is the backslash, right? You're solving X equal to B all the time. They make it as simple as possible. Whereas here, this is the solve for a linear algebra, and NP linear algebra solve A, B. Okay? Now let's talk about LU decomposition. How would I do an LU decomposition? So in an LU in Python, we're going to import SciPy linear algebra package. So this is going to give us access to some of these decomposition algorithms. And in fact, here's how you get it. SciPy.linearalgebra LUA. This is the LU decomposition of A. And what it brings back for you are three matrices, P, L, and U. So the U and L and U matrices, like we've been talking about, and a P matrix, which is the permutation matrix. The permutation matrix tells you whether you had to switch any rows when it did the decomposition. If P is equal to the identity, then you don't have to worry about permuting anything, because in fact, it didn't have to switch any rows in the process of using this. So the way to think about it, remember if I showed you two slides ago, is that if you're going to solve AX equal to B, and there is a permutation that happened, then what you've got to do is you've got to also take the vector b and permute it. So you can matrix multiply, NP matrix multiply p and b. Now what happened is it took b and p switched the rows it needed to, which was consistent with the LU decomposition you had to do with this A matrix for taking care of any zero pivots. And then you can do YP linear algebra solve LB2 and linear algebra solve UY. So this is a two-step process. Remember, you have to solve LY equals B. And by the way, B2 is where you've switched the rows of B so that you don't have a zero pivot. So you solve Ly equal to B. Once you get Y, you solve Ux equal to Y, and that's here. Okay, and actually we don't want to use solve because solve is not smart. It does Gaussian elimination again, but we can actually trade this out to understand that there's a actual upper and lower triangular form here and just do back and forward substitution. MATLAB, here you go. Here's the command LUP. Notice that LU comes first, then the P, which is exactly backwards from the way that Python does it. So LUP, and you see LUA. There's your decomposition. Once you have it, you can do this, the following. You can first take the P matrix, multiply by B. This does the permutations you need, and then you backslash it with L. That gives you Y, and then once you've got Y, you say X is equal to U backslash Y. Two-step process, and by the way, the backslash is smart in MATLAB. What it says is, hey look, this matrix is already an upper or lower triangular form, so all I have to do is back substitute. So if you use the backslash here with these matrices, it will perform these operations in order n squared, okay? Whereas Python, we've got to work on that to make that happen. So that's how you think about using the LU, and so again, you only do this step here once for a matrix A. You don't put this in any loops, right? You keep the A outside the loop. You do the LU once, and then when you're solving the equations, this is what you'd put in the loop, because this is order n cubed, and then these guys here are order n squared. Okay, that's how you save time. So anyway, that's the main ideas behind LU decomposition. It's a nice technique. It starts to get us to thinking about how to solve AX equal to B in a fast way. And what we see here is after I've played that one-time upfront cost of order n cubed to get the L and the U for a given matrix, I can use it now repeatedly at order n squared, which saves me significant amounts of time for solving many linear systems. More details can be found at the website here, all the notes, code, everything else you need to download, as well as further lectures.